On today's episode, traditional design engineers work in a straitjacket, but there is a solution. Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. One of the best parts about working here at Engineering.com is the opportunity to meet so many smart people in industry. Now, software has always had smart people, but the traditional intersection between software and engineering, CAD/CAM, well, that's morphed into something much bigger and much more important than most people realize. Now, I was a panelist at a recent roundtable hosted by Dassault Systèmes, their 3D Experience Forum, where I commented on the current state of the art in software-assisted engineering, model-based systems engineering. Now, we've all been watching advancements in artificial intelligence, augmented and virtual reality, simulation, and generative design, but these technologies, although important, they dance around the fundamental core of engineering. Artificial intelligence does what human engineers do, presumably faster and with fewer errors. Augmented and virtual reality are the logical extensions of 2- and 3-dimensional rendering. Simulation is the virtualization of hardware-based R&D, and generative design is simply the automation of what every design engineer does every day in developing new parts and assemblies. Now, they're all essential, but they don't fundamentally change the way engineering is done. Now, model-based systems engineering, however, is different. This is about removing the handcuffs that constrain every modern engineering project: documents. System complexity in engineering has always been a problem, and with the advent of commercial digital computers in the 1950s, major defense programs became too complicated to effectively manage. Now, determining the critical path on a large Gantt chart was the only way to handle most problems, and the need to police revision histories on thousands of individual part and assembly drawings, plus associated documents related to testing, regulatory compliance, quality, and scheduling within major projects, well, that basically guaranteed that projects would come in late and over budget. Cost, delays, and the root problem of getting dozens or hundreds of engineers' designs to come together into sub-assemblies, assemblies, and final products, well, it's been a perpetual issue, whether the project was an electric toothbrush or an Apollo moon rocket. But why? In my opinion, there are two primary reasons. The first was, and is, simple. Projects are costed relatively early in the design phase, and there's no way to effectively predict how much redesign may become necessary, or in the event of a poor design making it all the way to production, the eventual cost of rework. Now, for large projects, especially in defense, the only way to get a big project across the finish line was either to price new projects at astronomical levels or negotiate cost-plus contracts, or both. Now, the second reason was and is simple. With each individual engineer responsible for one part or one subassembly of a large project, their motivation and their metric of success is determined by the functionality, cost, and optimization of the single thing that they work on. Integration of that part into large complex assemblies like airplanes or automobiles, well, that was typically handled by a different engineering team responsible for integration. The result was the inevitable negotiation and horse trading to get parts into subassemblies and then into assemblies and on into products. Now, all of this costs time and money. The brilliance of model-based systems engineering is that a single digital concept of a large and complex product is accessible to everyone at every level of product development. An engineer may be responsible for a flange or bracket, for example, but he or she has the ability to see how it fits into the larger project, and also sees what the ripple effects are of engineering changes all the way through the process, from design revision to manufacturing. Now, this is incredibly powerful, and it adds a real incentive for engineers to think holistically about every step of the design process. Want to add a lightning hole to take mass out of that hypothetical bracket? Well, what if that design change affects the flow of cooling air past a circuit board? With model-based systems, difficult to predict outcomes can be simulated and revealed before production begins, and with the transparency of the process, everyone can see that impact. Now, in this simple example, a change to another component or assembly might allow that hole without compromising performance and reducing overall cost at the same time. But with engineers working in silos with traditional document-based systems, there's no way to know how a small change can have big system benefits, so suboptimal designs are almost guaranteed. Model-based systems engineering has other benefits, and we'll be talking about that more here at Engineering.com. And if you're interested in hearing what I had to say in detail at the Dassault Systèmes 3D Experience Forum, the link to that video is in the description below. In the meantime, think about model-based systems and think hard about how much document-based systems put engineering professionals in a straitjacket. Well, that's it for today's episode of End of the Line, brought to you by Engineering.com. If you like this show, be sure to subscribe to our channel and click on the notification bell for our next episode. For our deeper engineering video series for the manufacturing professional, visit engineering.com TV to watch exclusive shows like Manufacturing the Future, not found here on our YouTube channel. The link is in the description below. Thanks for watching.